So here's an example of a power series, and we're going to ask where this power series converges. By the way, let's just make clear what this is, what sort of power series this is. I could rewrite this as the sum from n equals 0 to infinity of 1 over 2 to the n times x to the n. So that makes it clear that this is going to be an, and this is our x to the n term, and you can see that this has a center of 0 because it's not like x minus 5 or x minus 7, it's just x, so this has a center of 0. So we're going to ask where it converges. This is how we do that. What we're going to do is use the ratio test on the general term of the series. So we're going to use the ratio test. This is actually one of those series where you could use the root test. I like to reinforce the idea of using the ratio test because usually when people choose the root test, they've overlooked something and it becomes very difficult to evaluate. This is certainly a series where you could use the root test, but I want to demonstrate with the ratio test how it works. So let's use the ratio test, and what we're going to do is calculate the limit as n approaches infinity of, I need the general term of the series, but with n using n plus 1 instead of n. So this is going to be x to the n plus 1 over 2 to the n plus 1 over x to the n over 2 to the n. Oh, and also I should use absolute value around that. Turns out that there's really nothing, I shouldn't say there's nothing negative because we don't know what x is, so I'm going to keep the absolute value in there. So this is going to be the limit as n approaches infinity. Simplifying this, I get x to the n plus 1 over 2 to the n plus 1 times 2 to the n over x to the n. And I just want to simplify this a little bit more to make it easier to evaluate. This is going to be 2 to the n over 2 to the n plus 1 times x to the n plus 1 over x to the n. So we can see now what sort of cancellations we're going to get. So this is going to be the limit as n approaches infinity of 2 to the n over 2 to the n plus 1 is just going to be 1/2 once I do the exponent subtraction, and this is going to be x to the n plus 1 over x to the n is x. So since there's no longer an n in this expression, I can, by substitution, even though n itself looks like a variable, since n doesn't appear in this expression, as far as this limit is concerned, this expression is a constant. X is not the variable that's moving in that limit, so we don't need to account for it when we calculate the limit. This just becomes x over 2. Now, what that means is that, so we've got this limit. The ratio test limit is x over 2. Normally what we've done is we've calculated a numerical limit and simply asked whether it's less than or greater than 1. In this case, what we know is that the ratio test will produce a convergent series as long as the ratio test limit is less than 1. So what I want to do is actually set x over 2 to be less than 1. That gives us absolute value of x is less than 2. So what we can see is that the series converges as long as the absolute value of x is less than 2. Now what does that look like? Absolute value of x is less than 2 means that we're looking for this interval. And of course we know that power series always converge in an interval that has the center of the series at the dead center of the interval. We know that the center is 0, and that's exactly what we see here. So that's the center of 0. The interval is -2 to 2. So what we know at this point is that the series converges for at least -2 x values that are in that interval. What we don't know is what happens at the endpoints. So now we want to test the endpoints separately. So what we're going to do is we're going to test the endpoint x equals 2. What we're going to do to test it is we're just going to substitute it into the original series. The series is this one, x to the n over 2 to the n. So if I substitute x equals 2 into the sum from n equals 0 to infinity of x to the n over 2 to the n, what I get is the sum from n equals 0 to infinity of 2 to the n over 2 to the n. That equals, when I divide that, I just get the sum from n equals 0 to infinity of 1, which is just like 1 plus 1 plus 1 plus dot dot dot. You can easily see that this is going to come out to infinity, but let's do it formally. How do you prove that this series diverges? The simplest test to use is the nth term test. We're just going to use the nth term test. And notice, by the way, I'm not using the ratio test. I'm not using the root test. Why? Because look how I got this number. Look how I found that 2 and negative 2 were important. I got them by setting x over 2 to be less than 1. 2 is the point where this number is equal to 1. That's the point where the ratio test is inconclusive. That's the definition of what the endpoints of this interval are. We find them by finding the place where the ratio test gives us 1 or inconclusive. That's why you can never, ever, 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 ever use the ratio test to find whether the series converges at its endpoints. I read this all the time on the final exams. People say, like, by the ratio test the endpoints converge, and it's just wrong. It completely misses the point. So anyway, we're going to use the nth term test. We're going to take the limit as n approaches infinity of 1, because that's the general term of this series once we replaced x with 2, and limit as n approaches infinity is 1, which is not equal to 0, and therefore we get diverges. X equals negative 2. We're going to test that endpoint. So we're going to substitute x equals negative 2 into n equals 0 to infinity, x to the n, 2 to the n. That gives us the sum from n equals 0 to infinity of negative 2 to the n over 2 to the n. A little simplification will give us negative 2, that'll give us negative 2 over 2 to the n, which is just negative 1 to the n. Well, we know what that looks like. That's just going to be 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc. This doesn't go out to infinity. It just keeps oscillating back and forth between, when I add up the first term, it's 1. When I add up the first 2 terms, it's 0. The first 3 terms is 1. The first 4 terms is 0. The first 5 terms adds up to 1. The first 6 terms adds up to 0. So what we can easily see is that this is equal, well, it doesn't equal anything, but the partial sums are either going to be 1 or 0 depending on whether we're adding up an even or odd number of terms. What that means is that you can see that the limit as n approaches infinity of negative 1 to the n does not exist. So because this term is because this term is going to be either positive or negative 1 depending on whether n is an even or odd number. A limit that doesn't exist cannot be equal to 0, and therefore the series diverges by the nth term test. Another way, incidentally, that we could have gotten to this is simply observe that this series and this series actually are geometric series with, this has r equals 1 and this is r equals negative 1, both of which would have also been a perfectly valid explanation of why these series diverged, of why these specific series diverged. So we can see is that the interval of convergence does not include its endpoints, and we finally conclude that the interval of convergence is negative 2 to 2. That's the answer. Let's see if I can get this whole problem here in very small. There we go.